Okay, welcome back. Now we're gonna talk about chemical messaging system. Um, in the last video, we looked at the format in which information gets carried in a given neuron, and we call that an action potential. It's the electrical way of transmitting information from one point to another in a given neuron, and that is on an axon. Today, we'll talk about the chemical messaging system. It is a way of communication that happens within, and not within a neuron, but between two adjacent neurons. As you can see, the information in a given neuron passes through the length of the axon, going from one node of Ranvier to another node of Ranvier till it reaches the end of the neuron, and we call the terminal button. Right, and this terminal button is attached to the dendrites of our next neuron, but there is always a gap between them, and we said that gap is called a synapse. And so a synapse has two neurons participating in it. Number one is the first neuron. There is an actual gap called synaptic gap, and the neuron, the first neuron, which is bringing information to the synaptic cleft, called the presynaptic neuron, and the postsynaptic neuron, which is about to take the information away from the synapse. A presynaptic neuron in its terminal buttons has several synaptic vesicles. And these synaptic vesicles are like sacs that contain the neurotransmitters. These are molecules of neurotransmitters. When the information from the given neuron reaches the end of the terminal button of an axon, as you can see, it pushes the synaptic vesicles to the end so that the membrane of the synaptic vesicle fuses with the membrane of the terminal button, thereby opening the vesicles out into the synaptic cleft, which results in release of these neurotransmitter molecules into the synaptic cleft. Following this release is this binding between the neurotransmitters and the postsynaptic neurons. As you can see, the neurotransmitter molecules go to specific sites on the postsynaptic neuron, and we call these sites postsynaptic receptor sites. So we can divide this transmission of information between two neurons at a synaptic junction into three important steps. Number one, the presynaptic neuron, it synthesizes synthesizes the neurotransmitters and stores them in synaptic vesicles. And once it gets information from the axon, once information reaches the end of this terminal button of the presynaptic neuron, then there is this release of neurotransmitters into the synaptic cleft. The third step is binding, where these receptors get bounded to the specific receptor sites of the postsynaptic neuron. What happens after this is this binding results in some specific chemical changes in the postsynaptic neuron, and that either results in or not of another action potential being generated in the second neuron. But the point is, this particular binding results in some chemical changes in the postsynaptic neuron. So that the information is transferred, the question is another action potential generated or not in the postsynaptic neuron? And we'll talk more about that. But before we move on to the factors that determine whether or not the postsynaptic neuron fires again in response to this message from the synapse, I just want to talk about what happens to these chemicals right here, because not all the neurotransmitters will be fortunate enough to actually get attached to these receptors. There'll be more of neurotransmitters that are left to float in the synaptic cleft. The question is, what happens to them? Well, there are several things that may happen to them. Number one, these neurotransmitter molecules may get deactivated or removed by some enzymes, or they just move away and disappear from the place. Or another possibility is that the additional neurotransmitters are reuptaken. They are absorbed back by the presynaptic neuron. So it's like a recycling process. They process it, make new vesicles, and form and reuse these molecules for another round of synaptic messaging. Another possibility is that the postsynaptic neuron can actually control the receptivity of these receptors, either to readily accept the neurotransmitters or not. And we call this a neuromodulation. So this is in a nutshell what happens and how the information gets transferred between neurons. So to sum up, we have seen that the information within the nervous system is transmitted in two different ways. One way is through electrical messaging system, which is the way of transferring information along a given neuron within a neuron, where the information passes from one node of Renvier to another. And once it reaches the end, the information then passes in the form of chemical format and with the help of neurotransmitters. Now, if you remember in the last slide, we said once the information passes from the terminal button of the presynaptic neuron to the next neuron, the question is, does it result in the generation of an action potential at the axonal hillock of the next neuron? Now, there are several factors that determine whether or not this happens, but there are two words I'm going to use here. Either the chemical changes in the postsynaptic neuron will result in the generation of action potential or not. And if it is generated, we call such neurotransmitters excitatory neurotransmitters. In other words, they are influencing or facilitating some changes in the postsynaptic neuron such that it will eventually go through the depolarization and repolarization. Okay, so you can see all these three connections are resulting in the generation of an action potential. This is just an example. Another possibility is that these chemical changes in the neuron as a result of neurotransmission here may be such that the chemical changes in the postsynaptic neuron will not result in the generation of an action potential. And we call such neurotransmitters inhibitory neurotransmitters. So so it is not necessary that the postsynaptic neuron fires again and the process continues. It may either fire or not fire. In fact, when inhibitory neurotransmitter reaches a postsynaptic neuron, instead of going through a process of depolarization, the next neuron actually goes through a process of repolarization. And there are several factors that determine whether it should go in one or the other way. And this is not a class where we can talk about the specifics. But if you want to know more, just to give you some additional information, of course, it's not in your for your quizzes, is that the depolarization happens because, as you already know, of the influx of sodium into the neurons, right? The opposite of which is hyperpolarization. This happens because of the exit of potassium. and or exit of other molecules. Now, so as we just said, the neurotransmitters can either act as a inhibitory neurotransmitters or excitatory neurotransmitters. Now, here's the caveat: not all neurotransmitters are excitatory. Not all neurotransmitters are inhibitory. Some are purely inhibitory, some are purely excitatory, but there are some that act differently at different times at different places in the nervous system. So there are several factors that goes into determining their actual effect on the postsynaptic neuron. A common example is acetylcholine or acetylcholine. This is an excitatory neurotransmitter, but it also acts as an inhibitory neurotransmitter. So its effect depends on the organ it's affecting. An example for an inhibitory, purely inhibitory neurotransmitter is endorphins. Endorphins, they reduce the activity, they inhibit the action potential in the organs, and these neurotransmitters have a natural pain-killing action. And if you are a runner, you would understand what I'm saying here is you feel this euphoric feeling when you're after your long run. That's because of these endorphins, natural neurotransmitters that act as painkillers and also give you a pleasant feeling. That's why often runners want to run more and more and more and more. Well, here's the question: what else gives you a euphoric feeling? Well, you're right. How did you know that? Yeah, I'm talking about morphine. Okay, if you didn't think about it, I'm sorry, but morphine, remember morphine, you know what it is? Especially if you or somebody else went through a procedure and they need pain medication, and morphine is often prescribed. So it acts as an endomorphin or endorphin, but it actually reduces the pain and also gives some weird euphoric feelings. Now, the neurotransmitters are required to function normally for you to carry on normal activities. Sometimes there can be a chemical imbalance in neurotransmitters amount or its action, either in one or the other direction. There will be more neurotransmitters or fewer neurotransmitters, or their activity is increased or decreased, resulting in several disorders. We're going to just list them here. We're not going to talk about the specifics, which we'll do later. An example would be a neurotransmitter like dopamine. Then it is related to disorders like Parkinson's disease, schizophrenia, and addictive disorders. Then we have neurotransmitters such as norepinephrine, which is associated with depressive disorders. Then there is serotonin, which is very closely related to several depressive disorders. Then there is OCD and eating disorders. Then there is GABA, neurotransmitter, and it is associated with anxiety disorders. Again, we'll come back to these disorders and the role these neurotransmitters play, because neurotransmitters increase or decrease in amount can cause different kinds of disorders. And another example is acetylcholine and its relation with Alzheimer's disease. And so natural neurotransmitters have some usual function to a role to play in our usual day-to-day activities, right? But we as humans have learned ways to create drugs that act either in unison with neurotransmitters or against the natural neurotransmitters. And we have these new terms here: agonists and antagonists. An example for an agonist is a stimulant like caffeine, amphetamine, and cocaine. These are agonists. Agonists are those artificial chemicals that mimic the action of a natural neurotransmitter. Anti-anxiety drugs, also some of them act as agonists, and we'll talk more about these agonists and antagonists later. Some antidepressants like SSRIs, and we'll talk about those in a different video, they're also agonists. Agonists are, again, the artificial chemicals that act like neurotransmitters. Especially agonists are the ones that increase the availability of these neurotransmitters. Morphine and heroin is another example. An example for antagonists is antipsychotic drugs. Antipsychotic drugs, they decrease the availability and activity of a naturally occurring neurotransmitter, and we'll talk about that again later. Now, to see how agonists and antagonists work, if you think of the neurotransmitter itself as a key, and think of the receptor site on the postsynaptic neuron as a lock, there's always this one-to-one specific connection between a given receptor and its neurotransmitter. So not all neurotransmitters can fit in all the receptor sites. Only specific kinds of neurotransmitters can fit in specific kinds of receptors. So it's like a key and lock model. Now, natural neurotransmitters have their natural natural receptor sites, right? And they easily fit. Now, what an agonist is like a chemical that mimics the action of a natural neurotransmitter. So it easily fits the key and acts like an agonist. Now, there are several other ways a chemical can act as an agonist without actually blocking the sites. We will talk again about this later, but just keep in mind that what agonist is basically doing is increase the activity of a neurotransmitter. Agonist, on the other hand, it will decrease the activity of a neurotransmitter. One way it does is by blocking the lock of this neurotransmitter so that there is a decreased activity of the original neurotransmitter. So that's all in this video. In the next video, we'll look at neurotransmitters and specific disorders related to these neurotransmitters. And then we'll move on to the last topic, the nervous system, and look at the structure of the brain, spinal cord, and other related things. Thank you very much.